So, very good evening to all the participants, and welcome to this third day of a 1 week online training program on biostatistics and research methodology. Myself, Dr. Dharmendra Yadav, welcome to all of you. I hope you are enjoying this training, all the sessions. You can share your feedback on our email. So it's really a great privilege for all of us that our esteemed resource person of this today's session, Dr. Ashish Kumar Yadav, is with us. So we welcome you, sir, on behalf of organizing committee and behalf of participants and my own behalf.
Thank you, Dharmin.
So just before starting the session, we just want to introduce our resource person to the participants. So Dr. Yadav is presently working as assistant professor in the Center for Biostatistics at Faculty of Medicine, Institute of Medical Sciences, Banaras Hindu University, Varanasi. He has research interest areas like multi-level modeling, epidemiological design, regression analysis, survival analysis, meta-analysis, Bayesian statistics. He has completed his PhD from a renowned institute, that is National Institute of Medical Statistics. It's a ICMR Institute in New Delhi. He has completed his master's from Banaras Hindu University. And he has also a professional diploma from Clinical Research, CPDR, Catalyst Clinical Services. He has a teaching and research experience of more than 12 years from various institutions like ESI, Postgraduate Institute of Medical Sciences, Kolkata, and Jalwar Medical College, Jalwar, Rajasthan, and National Institute of Medical Statistics, ICMR, New Delhi. So he has various resources like experience from teaching and research institutions, as well as he has good software, expertise in various statistical software like R, Stata, OpenBooks, Python, Spaces, Tableau, etc. So thank you so much, sir.
Thank you, Dharmin,
for being with us and for giving your valuable time to the participants and to share your knowledge and expertise.
Thank you, Dharmin.
So, sir, we'll take the session on the different types of study designs in detail. So, thank you, sir. Over to you.
Okay. Thank you, Dr. Dharmin and the organizing team for giving me the opportunity to share my limited knowledge with you people. As Dharmin has told that I am working in the field of biostatistics. So, and the topic which is given to me is study design. And to be very frank, and study design is a very broad topic. To cover it in 2 hours is really difficult. But I will try to give you some insight of the study design so that you can pursue it and you can explore what's going on. So basically, I have divided the presentation into 2-3 presentations. First one is your overall tools which we are using in the study design. And then we would be moving to the study designs which are very important. For example, the analytical ones, especially I have focused on that, your case control study design, your cohort study design, what are the biases which may occur in this. And within the study design, we have a lot of issues while we are conducting it in terms of your confounding and in terms of your interaction effect and all that. So I will try to cover all these things, and I hope that you people will enjoy it. So let's start the presentation. Give me a second. Are the slide visible to everyone? Hello, Dr. Dharmin, can you confirm? Is the slide visible?
Not yet, sir. Please
Give me a second.
share your screen once again.
Okay.
The slide is not visible.
Give me a second. I'm doing it.
Okay. Thank you.
Okay.
Yeah, it's fine. It's fine. So we request the participants kindly mute yourself.
Okay. I hope now it is visible.
Yes, it's fine.
Okay. So basically, the study designs, analytical and your observational or experimental, has a aim to identify whether the risk factor which you are thinking or the factor which you are thinking is a risk. So that causality, it need to be established scientifically. We need to establish it. Okay, for that we have, based on the scenario, we have different types of study design. For example, if we are measuring the risk and the disease at the same point of time, the study is referred to as cross-sectional study design. As the name says, at a cross-section, you are measuring the disease as well as the risk, and you are trying to establish the association or the causation between the factors. For example, you are at your clinic and a patient has come to you and your interest is, say, disease, say diabetes. So you ask the person whether he or she is diabetic or not, yes or no, and then you ask the same thing. You feel it's known that diabetes has a association with the family history. So you would ask him whether your parents are diabetic or not. So disease as well as the risk are measured simultaneously at the same point of time. Then we are referring to it as a cross-sectional study design. Now, what happened? The patient, second scenario is that it is a different situation in which the association is assessed. A second scenario is that the patients are admitted in the hospitals and one is having a visit and patients are of stroke, and the patient has already got the disease, and now you are asking them about their past experience about the risk factor you believe may be contributing in the disease acceleration is, say, smoking. So you ask him whether he or she was a smoker in past. Okay, so he or she may say that yes, I was a smoker, or very previously I was a smoker, now I'm not a smoker, but previously I used to have a smoking. You be a smoker. So in that case, we have the disease, and retrospectively at the back we are looking the disease outcome, whether it is there present or not. In that type of study design, we generally move from case to disease to your risk factor exposure. So we call it as a case control study design. And in a third scenario might be there, the individual is perfectly healthy. Okay, and you are observing him over a period of time, and you find that after a certain period of time, the group of students, say, or a group of school going students in your neighborhood, uh, they you are observing them to continuously. After a certain period of time, you find that out of the some students, few have developed not a very good lifestyle habits, and they are having say lifestyle pertaining to smoking, and some are there who are not having this type of habits. Later on, you find after some period of time that in the exposed group, few individuals have developed lung cancer, and few individuals who were in the controlled group, they have also developed the disease and non-disease. So here we are moving from exposure to the outcome, that is disease. So it is prospective in nature. So we called it as a cohort study design. Okay. So these type of studies are basically observational studies, which we have basically do not add much in establishing causality. So to establish a relationship which is very strong in nature or statistically significant, we need to have at least analytical study design, or we can have the RCTs also. Okay, so what are the tools which are used in these types of study designs? We are focusing first on them. So coming on the assessing risk factors. Okay. Okay. So all of you know the definition of epidemiology. I'm not going into that, but there are various definitions which are pertaining to epidemiology. Okay, but different authors, all the authors actually agree on three specific points. The first one is that epidemiology is the study of disease frequency. The second is that epidemiology is the study of distribution of diseases or risk factor. And the third one is it's the study of determinants. Okay, so in short, we can say that the study of distribution and determinants of health related states or event in a specified population, and the application of this study to the control the health problems can be said as a general definition of epidemiology. Okay. I think the slide is not changing by. Okay. So what is the aim of epidemiology? So according to IAA, that is International Epidemiological Association, epidemiology has three main aims. First one, to describe the distribution and magnitude of health and disease problems in human population, to identify the etiological risk factors in the pathogenesis of the disease, and to provide data essential to the planning, implementation, and evaluation of the services. So in general, the essential aim of epidemiology is to inform health professionals and the public at large in order to improve the general health status. So what is risk? So risk measures the probability of disease incidence. Okay. Sometimes risk is called absolute risk. Although risk is useful summary of the relationship between risk and disease, it is not sufficient by itself for assessing the importance of risk factor to the disease outcome. So in epidemiology, if you are thinking that a particular type of presence of particular variable in a group of individuals is a risk factors, that variable and the happening of event, that occurrence, that probability should be high. If that probability is not high, then we cannot say, or rather we cannot say that the particular event is should be considered as a risk event. So as I have said, risk is of two types: absolute risk and relative risk. Absolute risk, as it is, do not have much importance. Okay, because you are not measuring the risk with respect to any baseline figure. But if we are having a risk in the group of individuals who are exposed to the risk, and we are measuring the outcome with the individuals who are not exposed to that risk, and if somewhat we are getting a higher probability in a group of individuals who are exposed to the risk, then we may assess that the particular exposure is a risk factor. So relative risk or risk ratio is the ratio of the risk of disease for those with risk factors, that is exposed to the risk of the disease, for those without the risk factor, unexposed. That is, relative risk is risk in exposed divided by risk in unexposed. So it's a ratio. If RR is above 1, if you can see this red denominator, if it is equal to 1, it will be risk in exposed is equal to risk in unexposed. So agar 1 hai, so we would be saying that there is the risk, whatever you are assuming, is really not a risk factor, because when exposed or unexposed, there is no difference. But if you are getting a value higher, that is risk in exposed is more compared to risk in unexposed, that means your risk factor is a hazard, is having a hazard which is having a higher magnitude, so it should be considered as a serious concern. So that would be, in this case, your RR is a risk factor. If you are getting risk in exposed group lower compared to the risk in unexposed group, in that case, whatever the factor you are considering as a risk is not a risk one, but rather it is a protective factor. For example, vaccination. Individuals who are vaccinated would be maybe at lower risk compared to individuals who are not vaccinated against any disease. For example, in pediatric groups, we have a lot of vaccination going on. Okay. RR value, if we are getting more than 1, it doesn't mean that it would be significant. You will be saying that this much percentage higher risk we are having in exposed group compared to non-exposed group. Whether it is statistically significant or not, that we need to test it using testing of hypothesis. Okay. So in epidemiology, we are often interested in evaluating the chance that an individual who possesses a certain attribute also has a specific disease. The most basic epidemiological measures is the probability of an individual becoming newly diseased, given that the individual has a particular attribute under consideration. This is called the risk of the disease. The attribute considered is called the risk factor. Hence, the risk measures the probability of disease incidence. So risk, formal definition which we are having of the risk is number of cases of disease divided by number of people at risk. Okay. So why comparison group is vital? Because we want to establish that whatever the higher magnitude we are getting in the, whatever the risk factor which is in the background variable is already there, that we need to rule out. Because, for example, we are considering say stroke. Okay, environmental pollution is such a thing which is in the background, and we want to establish that whatever the additional risk we are getting, that is because of the particular exposure, say because of your smoking only. So we need a group which is exposed to smoking, living the same environment, and we need a group where a group of individuals are there who are non-smokers, but they are living in the same environment. So whatever the factors which we are getting is only because of the additional risk which we are getting is only because of the smoking, not because of the your environmental factor. Now, the question arises whether we should use a relative risk or your absolute risk. Okay. So generally, whenever we are establishing the association, we go with the relative risk. So as in most procedures in epidemiology, a comparison group is required. The simplest one is to take here is the group without the risk factor. This lead to the definition of relative risk. Relative risk is defined as the ratio of risk of disease among which risk factor is present, exposed, with the ratio of the risk of disease among which the risk factor is absent, that is non-exposed. We have already seen that if RR above 1, it's a risk. Your risk factor under consideration should be checked for statistical significance. If RR is less than 1, significantly less than 1, then also it has to be tested for statistical significance. There is a display of data from an incidence study. Incidence study, that means we are getting it's a longitudinal studies and we are getting new cases. Okay. So in that case, relative risk, as we have seen in the risk in exposed group. So this is our exposed group. In exposed group, what is the risk? So this is A disease divided by total number of individuals who are exposed. So number at risk. So number at risk is A plus B, A divided by A plus B. Okay. It's similar to that of probability only. In probability of happening of an event A, we say that favorable number of cases divided by total number of cases. Okay. For example, if I say in a pregnancy outcome, what is the probability of having a male? Okay. So favorable, only male occurs, and total outcome, that is male and female. So here also we are having the same probability of having the disease case from exposed group, that is favorable is A divided by total exposed, that is A plus B. So it is A divided by A plus B. Similarly, risk in unexposed group. So the risk in not exposed group is what? Not exposed group is C divided by C plus D. And then we have done the mathematical manipulation. It's A into C plus D divided by C into A plus B. So this is the formula for the relative risk. So relative risk is what? It is nothing, it's a disease, incidence of disease in exposed divided by incidence of disease in non-exposed. Okay, so by definition, the population risk is simply a probability, okay, and the standard error for if you remember that it's nothing but its probability is what? It's a type of a proportion only. Okay, and if you remember for proportion, we can estimate the standard error of proportion. It is P into Q divided by N. Okay, so the standard error for the relative risk is also same. Instead of P proportion, we are using the risk R into 1 minus R divided by N. And once we know that the point estimate and the standard error, we using 95% normal approximation, we can calculate the confidence interval. So the 95% confidence interval for the relative risk is nothing but its point estimate, that is the relative risk, plus minus 1.96 into standard error. 1.96 we are getting it from the standard normal distribution value, Z value. Okay, so once you know the relative risk, you can calculate the confidence interval of that relative risk. Narrower the confidence interval you are getting for the relative risk or risk under consideration, more power you may have in the inference that the risk under consideration is really an important factor. Okay, the this is for the risk. Okay, now for the relative risk, as you know, that it's a ratio of two risks. So the confidence interval for RR is slightly more difficult to compute compared to your R risk. The distribution of the sample RR is skewed, and log transformation is necessary to ensure the approximate normality. So in that case, for the risk, we have this is standard error formula. For your relative risk, that is the ratio of the two risks, we are having the formula standard error log transformation, which is equal to under root of 1 upon A minus 1 upon A plus B plus 1 upon C minus 1 upon C plus D. And we can calculate the 95% confidence interval using this formula, which is log E lambda plus minus 1.96 standard error. Okay, so we are using the log transformation. Why? Because we are using log transformation that initially the ratio of two risks is skewed one. We want to reduce the skewness. So we are using a log transformation. So once we are using a log transformation, then we are getting this confidence interval. And once the confidence interval, you have got the 95% CI, you can always transform, take the anti-log and get the absolute values. We will see one example. Okay, so lower limit is the value which we obtain by subtracting it, and upper limit is the value which we are having by addition of one plus factor of 1.96. Okay, and to have the actual limit, we are used to have the exponential of the lower limit as well as the upper limit. So let's look at the example. A small example is there. In 1985, employees of Electricity Generating Authority of Thailand have employees in the age group of 35 to 54 years old were asked to complete a questionnaire that asked, among many other things, whether they currently smoked or not. Okay, vital status, alive or dead, was ascertained 12 years the finding of the studies are presented below. So this is the finding of the study. Okay, so smoking and cardiovascular death in E-GATE studies. Smoker at entry, yes, no. Cardiovascular death during follow-up, yes, no. And we have got this study output, okay, cross tabulation. So we can easily calculate the risk in exposed group. Okay, so risk in the exposed group will be how much? It will be 31 divided by 1417. Similarly, risk in non-exposed group will be 15 divided by 1898. Okay, so calculate the overall risk if we have to calculate. So overall death we are getting 46 and total number of we are getting it as 3315. Okay, calculate the risk for smoker and non-smoker. So overall risk of the death due to cardiovascular disease is 46 divided by 3315. The risk among smokers is 31 divided by 1417. Risk among non-smoker is this much, and relative risk, as you know, that risk among smokers divided by risk among non-smokers. So we are getting it as 2.7682. Okay. Now we have to calculate the 95% confidence interval. So 95% confidence interval for risk of cardiovascular death for smoker. That means for the smoker group. So it is point estimate for R, not RR. So it's 0.0281. This is point estimate plus minus 1.96 standard error. Standard error, as I have told, it is R, which is 0.02817. 1 minus R divided by your number of observation, which is 1417, number of total number of this row total. This one 1417. Okay. Similarly for the your you can calculate it for your non-smokers also, how much you are getting. Okay. Now, as you see, we are having a relative risk as 2.76. That means you already know that they are having more than twice plus 76%, 276% higher risk among the individuals who were smokers. Risk of your cardiovascular death in smokers compared to non-smokers. And using the confidence interval, we can see that this value 0.01, it's having a very narrower interval, and it's not containing the null value. Null value means if you are framing a null hypothesis that whether the cardiovascular death and smoking are associated or not, what would be the null hypothesis? Can anyone tell?
There is no association of smoking with cardiovascular death.
Yeah, very right. And if we have to write it numerically, what we should write? RR is equal to 1.
Ratio equal to 1.
RR is equal to 1. So now you can see that you can see that in this confidence interval, this confidence interval is not containing the value of null. It's not containing the one value. So it is giving you an indication that your this hypothesis in this case will be getting rejected because it is not containing the null value. Okay. Of course, we have to do a hypothesis testing and then we have to test it. But confidence interval is also giving you an idea whether your null hypothesis will be rejected or not. Okay. Now, this is for the risk for smoker, and similarly we can have for the non-smoker. So for non-smoker, this will be our point estimate 0.007 plus minus 1.96, and standard error as we have done. We can calculate it for the non-smoker also. And for RR, what we have to do? For RR, we have to convert it into the logarithmic one. That means this value 2.7682, we have to take the log of this value. So whatever the log we are getting, that would be the log estimate of this one, plus minus, we have to use this 1.96 standard error of this one. Okay, so you will try to have the log value of these, and you can calculate the 95% confidence interval for the relative risk. Okay, so this is relative risk and very short. Now we will be moving to the odds ratio. Okay. As we have seen, the risk is a probability. Whenever a probability is calculated, it would also be possible to calculate an alternative specification of chance called the odds. Okay. So whereas probability measures the number of times the outcome of interest occurs relative to the total number of observations, the odds measures the number of times the outcome occurs relative to the number of times it doesn't occur. Okay, so as we have seen in the relative risk, that it's a type of, it is a probability only. We have number at risk, number disease divided by number at risk. Okay, favorable divided by total number of observation. So it's a probability. Sometimes what we are comparing, we are more interested in comparing that what will happen if we are comparing probability of happening of event divided by probability of not happening of disease event, which we are calling it as a odds. Okay, so odds is number of cases of disease divided by number of non-cases of disease. Okay, so odd can be calculated for different groups, the odds for those exposed to the risk factors and the odds among those who are not exposed. So in odds ratio, what we are calculating? We are calculating two different ratios. In the numerator, we are having odds in exposed group divided by, in the denominator, we will be having odds in non-exposed group. Okay, so for example, in this, suppose this is a incidence study design, okay, longitudinal one. So probability of disease happening will be A divided by A plus B. And probability of non-happening of disease will be B divided by A plus B. So this will be the odds in exposed group. Okay, you can see. So odds in exposed group is your A divided by A plus B, and for your non-disease, it will be B divided by A plus B. And if we are taking the ratio, A plus B will cancel out. So we would be getting the this odds in exposed group as A by B. Similarly, we would be getting an odds in non-exposed will be how much? Probability in of happening of disease in non-exposed is C divided by C plus D, and for no disease it would be D divided by C plus D. C plus D will cancel out, and it will be odds in non-exposed group is as C by D. And if we are taking these two ratios cumulatively, we are calling it as odds ratio. Odds of happening of disease in exposed divided by odds of happening of disease in non-exposed. We should never remember the formula that it should be AD by BC, because if ABCD is getting changed in your data set, everything will be changed. Okay, so we have to go with the concept that odds ratio is odds of happening of disease in exposed divided by odds of happening of disease in non-exposed. I hope I am clear to it. Okay. Anyone having confusion in RR or OR so far? Okay, someone has.
So, sir, if you are having any data like the one which is shown in the screen, so we will calculate both the ratios.
Yeah, you can have that eGate study data, the previous one which we are having. This one, sorry. I have done a cross tabulation and then we have given it. This data you can have and you can calculate. You can calculate the OR as well as you can calculate the RR, and you can calculate the RR confidence interval. OR we will be discussing now. Okay.
Okay, sir.
Okay. Now, as with RR,
so sir, which is better, like OR or RR?
Ma'am, I'm coming on that thing. It depends on a lot of things. Okay.
Yeah, sir.
We will compare it. Okay,
yes,
we will
sir.
compare it. Okay. So as with RR, the distribution of odds ratio is better approximated by normal distribution if a log transformation is applied. Okay, so as you can see that whenever we are taking a ratio of odds, or if we are taking the ratio of the risk, relative risk, the data becomes little skewed one. Okay, so we need to transform it, and that's why we are taking a log value. And to have the absolute value, we would again take the exponential. So standard error for the log 1 odds ratio, we can calculate it as under root of 1 upon a plus 1 upon b plus 1 upon c and 1 upon d. So to calculate the 95% confidence interval, we need the point estimate, that is the log of odds ratio. Odds ratio, whatever we are getting, we will be taking the log, converting it to the log scale, minus 1.96, standard error of log, this one. Similarly, for the upper limit, we would be having point estimate plus value, and we can have the absolute values by transforming it to exponential. Okay, so you can calculate the OR with 95% CI for the table 1, this one, you get data. RR, for RR, we have already seen. For OR, you can calculate and see what difference you are getting for the same study design, which is prospective one in this case. I hope you can calculate the values. Okay. Now, as we all are interested whether we should go for a relative risk or odds ratio, what is going to change? Okay. So as we have seen, risk and odds ratio measures the chance of disease incidence in some way. Thus, relative risk and odds ratio measure comparative chance. Risk is preferred measure because it is a probability. Relative risk is a probability measure, or in a easier sense, we can call it as a proportion. So proportions are directly, you can is easy to understand, but once we are calling it as odds, it's little less understood compared to your proportion. But in some cases, RR are having a upper hand. Okay, and in some cases, often it is not possible to calculate the relative risk. So in logistic regression analysis, it is convenient to calculate directly. You can calculate the OR, but you cannot calculate the RR. So RR, as the definition, if you remember, it is incidence of disease in exposed divided by incidence of disease in non-exposed. That means you need a incidence value, newer cases value. Often it is not known whether the disease, whatever the study situation, may not be able to provide you the new number of cases. So in that case, if you are not having the incidence value, you cannot calculate the relative risk. In that case, you have to go for a odds ratio only. So although easy to understand and more practical values we will be having from the relative risk, but often the data, because of the data limitation, we are having the odds ratio at our hand. Okay, prospective study designs, to conduct a prospective study design, it's time taking and is very costly affair. But to conduct the study design where incidence values are not very important, in that case we can have the easily we can have the value of odds ratio. So sometimes what happen that odds ratio can be a very good estimator of relative risk. In that case, if someone is designing a prospective study design, it would be a waste of time. You can easily do the things using your retrospective study design, that is your case controls. So odds ratio may be a good approximation of relative risk whenever the disease in question is rare. Okay, so when the disease is rare in nature, RR would be a good approximation of OR. Let's see how it is. So if the disease is rare in nature, instead of using your OR, will give you a good value of RR. So let's look at this table. So in this table, suppose you are having a data from the incidence study and the disease is rare in nature. So when the disease is rare in nature, this A plus B, maximum magnitude will be of non-diseased B. So we can approximate A plus B as B. And for the non-exposed, maximum C plus D, maximum will be D, which is C plus D can be approximated as D. And in this case, if we are using the formula AD by BC. And if you are using the formula for your relative risk, if you remember the RR, for RR, we were having this formula, A into A divided by A plus B, C divided by C plus D. That was for your A into C plus D divided by A plus B into C. So if C plus D, A plus B will become your how much? B, and C plus D will become your D. So your odds ratio is same as that of your RR. So if the disease is rare in nature, this relative risk formula, this one, if you see, this formula of relative risk, C plus A into C plus D. This C plus D will become D. So it will be AD, and this A plus B will become B. So this will be BC. AD by BC, the same one which we are getting for OR. So in that case, if the disease is rare in nature, you can easily approximate RR from OR values. Okay. Compared to out of the RR and OR, which one is more reliable? Generally, RR is more reliable compared to your OR. Whenever you will find that for the same type of study design, if we are calculating a RR value or OR values would be little extreme. For example, if OR values will always be greater than RR values whenever RR is greater than 1. OR values will always be smaller than RR values when RR is less than 1. And when they are equal, then it's a good approximation. Okay. So taking these conclusions together, the odds ratio is always more extreme than the relative risk. Okay. For the same data set, if we are calculating table number 1, if quickly someone can calculate and tell me what values you are getting for OR and RR, this one. So RR we would be getting, OR we would be getting 31 into 1883. RR value I think we have given. RR value is 2.7682. Okay. Now you can calculate the OR value for this. So for OR value, it will be 31 into 1883. 31 into 1883. So we are getting 58373. That is the numerator, 58,373. Okay. And for the denominator, we are having 15 into 1386, which is 20,790. 20,790. So numerator which we were getting 58,300, and that this one we are getting it as 27,000. So how much value we are getting? 31 into 188.
2.8.
2.8. Thank you. So you can see that for the same value, we are getting this as 2.7, but we are getting a 10% higher risk when we are calculating it as OR. And if it is a protective one, we would be getting a lower value. Okay. Okay. So this is another example. You can calculate the OR and RR values, and you can check that your OR is more extreme compared to your RR. So generally, there is a relationship between OR and RR. When the risk in unexposed population is very low, okay, suppose equal risk is there in exposed and non-exposed. If we are having a 1, no risk, then RR and OR are equal approximation. Whatever the value of RR you are getting, you would be getting the same value for OR also. This line of equality 1. When the risk in unexposed and exposed is equal, same 0. When the risk in unexposed population is 1%, this line. The risk in unexposed population is 1%, then you can see that more or less it is close to the line of equality. When the risk is in the unexposed population is 5%. Okay. Now, when it becomes 5%, you can see that for RR value of 4, we are getting a OR value which is around 4.5, above 4.5, 4.7 exactly we would be getting for this one, for 5, this one. Okay. So you can see, and as the risk in unexposed population is getting increased, even for a smaller value, if the risk in unexposed population is 30%, in that case, you can see that if we are having a RR value which is equal to 2, we are getting a OR value which is equal to 5, more than twice, almost thrice values we are getting. So the relationship between RR and OR depends a lot on the disease proportion, number of individuals who are disease, how common the disease is in the population. If the natural occurrence of the disease is very high, okay, higher proportion, then automatically if the for a lower value of RR also, you would be getting a higher value of OR. Okay, I hope this is clear. In this case, you can see that we are having lower disease, unexposed population risk. So in that case, if we are calculating it, we would be getting the difference in OR and RR. Whereas if you keep on increasing the disease prevalence, as it is getting increased, the magnitude will vary according to this chart. Okay. So, and there is a reason why we are considering RR as a better approximation compared to OR. Okay. Let's look at this example, small example. In this example, if you calculate the OR value, in here we are studying the relationship between peripheral vascular disease and cigarette smoking. Okay, and if you can calculate, you will see that in this table number 3.4, you will not be getting a significant RR value. Okay, if we are calculating the odds ratio. So what the odds ratio is doing? Actually, the odds ratio, in odds ratio, you are not knowing the exposure completely. Okay, in this case, there are many smokers who have just quit the smoking habit. Okay, and since it is not a follow-up study, you cannot segregate them in ex-smokers or current smokers or never smokers categories. So in that case, if you are having only two categories, disease present or absent, risk factor present or absent. Okay, in that case, your OR value will not give you the exact good idea about the actual risk of the disease. So for the actual risk of the disease, it's very important that we should focus on the incidence value. That means we are having a longitudinal study design. So for example, in this, if we are having a longitudinal study design, we are able to classify that the smokers who are the current smokers, who are the ex-smokers, and who are the non-smokers. And if then we are calculating compared to never smoker, what is the risk in current smoker, and compared to never smoker, what is the risk in next smoker, we would be getting a higher value of RR. Okay. Another test.
So, sir, for RR, incidence values are important.
Yes, yes.
Okay, sir.
In study design, incidence values are important for OR as well as for RR. Okay. Fisher exact test. Okay, this is a test. All of you have not written the chi-square test because all of you are familiar with that test, I feel. The Fisher exact test is a test if the expected cell frequencies are less than 5, then we are using the Fisher exact test. Okay, so it is generally used in a 2x2 contingency table, and we are using this test statistics given in equation 1.1 to test whether the risk factor and your disease are associated or not. This is another example. Here we are having the disease frequency is less than 5. So we can use a Fisher exact test and we can find out whether the there is a relationship between hypertension and activity. Another important, very important problem which I want to discuss with you people is that what is the effect of trend? Okay. Risk is generally not dichotomous in nature. Present or absent, we used to have it, but many times an individual is there who is having just one cigarette in a day. Another individual is there who is smoking 5 cigarettes in a day. Another individual is there who is having a pack in a day. Okay, so we want to check the trend. What is the effect of the magnitude of the risk? If the magnitude of the risk is getting increased, how the risk is going to increase and how to ascertain that thing. Okay, so generally, often what we do is that we generally try to have only 2 levels. Okay, for example, in this one, we have only two levels we consider, exposed and non-exposed. But what happened in often the exposure group has many levels. Okay, so if exposure groups are having many levels, how to calculate the actual magnitude of the risk? Okay, so this is for the just the 2 levels, 1 versus 2. What one thing we can do, if there are several levels, we can compare 1 versus, we can choose one as a baseline. Social class classification is there. So upper class compared to second one, upper class compared to third one, upper class compared to 3 lower one, upper class compared to the 4th one, and upper class compared to the 5th one. This is a technique at 2 levels we can do it, but how we can do it simultaneously, that we are going to see. Okay. Okay, so the choice of the base level is arbitrary, but there is no statistical argument that the base level should be chosen as that level with risk or odds that has the smallest standard error. So if your science is telling, if you know the problem, and if you are, then you are choosing a particular group as a base level, it's okay. But if you are not having any idea that which level should be considered as a base level, in that case, the group which is having smallest value of standard error should be chosen as a base level, and compared to them, you can calculate the risk in the other groups. Okay, so continuous risk factor. So far, we have seen that the risk is in dichotomous type, present or absent. But if suppose the risk factor is not a dichotomous type, it is a continuous variable. Okay, generally, for example, if I say the if you see, there are certain variables which are continuous in nature. For example, your systolic blood pressure, diastolic blood pressure, they are very continuous in nature. But for the proper management, what we are doing is we are classifying them, that if the value is above 120, we will be calling it as in a risk. If it is more than a particular value, then we will be calling it as a stage 1, stage 2, like that. But the variable as it is a continuous one. Okay, so if somehow you are having a risk factor which is at continuous level, then how we can measure the actual risk in our modeling of your study design. So here we are having a hypothetical data set. Okay, suppose we are having the risk factor as dose, and we are having 1, 2, and 3, and we are having the disease status as yes or no, dichotomous type. So one thing what you can do is that you can combine any 2 groups. For example, you can combine 1 and 2 as low, compare it with the 3 as high. Okay, or you can choose 2 and 3 as high and compare 1 as a low one. Okay, in this is a hypothetical data set, and if you are calculating combining 1 and 2 and 2 and 3, your inference is getting changed. Okay, but often what will happen that on the basis you are classifying or categorizing your data set, certain information is lost, and you might whatever the information you are getting might not be true. Okay, there would be question on how you are going to group your data set. Okay, so the ideal way is that if your science is suggesting you have a pre-existing standards, for example, in BMI, BP, sugar, all that, we have a pre-existing standard classification table and we are using it, it's okay. But if we are not having a standard classification, in that case, what we can do is that we can divide it into equal intervals. But again, it in physical sciences subjects, it is quite good. But in medical sciences, generally the risk cannot be divided into equal groups. For example, if I am considering under 5 mortality, I cannot divide the hazard of under 5 mortality 0 to 1 same magnitude, 1 to 2 years same magnitude, 2 to 3 same magnitude. We cannot do that because we know that in 0 to 1 we have the maximum risk. Okay, but in some physical sciences you can do that things. Okay, so often the problem of grouping is very, very important. So how we are going to do it? So we can do it or we can test it. If our exposure is at certain levels, we can use a test of linear trend to find out whether the magnitude of the risk which is increasing is really effective or not. So in epidemiology, we are often interested in the dose response effect. That is the situation in which an increased value of risk factor means a greater risk of or the greater likelihood of the disease. It is possible to use a chi-square approach to test for the dose response trend whenever L levels of the risk factors are graded. So here we are not having just 2 levels of the risk factors. We are having L levels of the risk factors, and we are trying to assess the risk, cumulative risk. The theory behind the procedure is based upon the idea of simple linear regression. Consequently, we denote the results as test of linear trend. To apply the test, we first need to assign a respective score for each levels of the risk factor. These should reflect the ranking order. Okay, for example, in table number 2, could be rank it from 1 to 6. This one, table number 2, this one. So here you can see that for the risk which we are calculating as socioeconomic status, we are having 6 levels: 1, 2, 3, 4, 5, 6. So for first thing, what we have to do is that we have to assign it certain order, and we have to assign it some numerical value to this based on the ascending order. Okay. So once in this case, we are having 6 ranks, class 1 to class 5. 3 is having 2 ranks, so we are having total 6 ranks. So first, what we would be doing, we would be assigning a score, okay, which would be ordinal one, okay, and then we are going to calculate the test statistics using this formula, which we are having T1 minus N1 T2 divided by N the whole square divided by V, where T is A1 into Xi, T2 is Mi into Xi, T3 is equal to Mi Xi square, and your V, for the V, we are having this formula. Okay, so this is the test statistics. Using this statistics, we calculate the value of chi-square trend, and whatever the value you are getting, we are going to compare it with the chi-square distribution at 1 degree of freedom. Okay, so for example, in this data set, if we are assigning certain values, for example, look at this data set. Yeah, this data set. And suppose we are assigning the Xi values. Okay. And you need to calculate it. So suppose we are giving it certain values. So for the first class, suppose we have given a value in the ordinal scale rank. Suppose you have given it 1, 2, 3, 4, 5, 6 like that. Okay. So then, and you are having these values for the other one, disease present. So you can calculate this T1 statistics. You can take a this. Sorry, we have to every time we have to go back. You can take a snap of this data, and then we can try to solve it. Everyone can take the snap of this data set. Okay. Now you have got this values. X1 value 1, 2, 3, 4, 5, 6, 6, and diseased values. Disease status here, how many were diseased in X1 values? How many were non-diseased? And what is the total? Here, how many were diseased? How many are non-diseased? And M2 total. And using this display table, you just have to apply this formula. You have to calculate T1. T1 is A1 AI into XI. So you would be calculating AI into XI, this one. X1, A1, X2, A2 till the third one. Similarly, you are going to calculate the T2. T2 is equal to MI into XI. So MI, this one, into XI, this one. Total. X1, M1, X2, M2. Okay. Like that, you would be calculating T1, T2, and T3. T3 is nothing but XI square. And then we would be calculating the V statistics. So using this statistics, we are calculating to check the association. What we are going to test in this hypothesis, we would be testing the hypothesis that whether there is a trend, increasing trend, significant increasing trend with respect to the or whether there is no trend. Okay. So if we are getting a if our null hypothesis is getting rejected, okay, so null hypothesis H0 will be saying that there is no linear trend. HA will be saying that yes, there is a significant linear trend. Okay. As the risk magnitude is increasing, the disease is also getting increased. Okay. So if the null hypothesis is rejected, that means trend is important, significantly important. So we would be comparing this chi-square L value with the this test linear trend statistics value with the chi-square value at 1 degree of freedom. Okay. So this table number 2, can you people solve it? Table number 2.
Hello.
Yes.
Sir.
Yes.
Sir, I had a question that
Yes.
since we are checking the linear trend, then how do we come to know from the chi-square?
Come again.
Like if we are checking whether there is a linear trend or not, how we will come to know it from a chi-square data, because it is just supposed to test whether the goodness of fit is there or not, right?
Right. So goodness of fit, we are testing it, but we are what we are associating. If this test, if there is a linear information, a linear trend, that means if we are having initially there was no risk, then 10% risk is increased. So 10% higher risk means 10% higher disease prevalence should also be there. 20% higher risk, 20% more diseases will be added. Okay. For that, when you are measuring this disease outcome and the risk, if you are plotting them, you should get a linear line. If the relationship is non-linear in nature, somewhat your risk is such that if you are having no exposure, medium level exposure, the risk is increasing. Then if you are increasing the magnitude of risk again, but the cases are dropping down, that means you are getting a parabola shape. If you are getting somewhat the relationship is parabola type, then you cannot use this test. But if you are having the relationship which is linear in nature, that means if you are increasing the number of risk factors, magnitude of the risk, say smoking, 1 cigarette, 2 cigarette, 3 cigarette, like that, and if you are getting the number of cases of the cardiovascular vascular disease also getting increased, then it is a linear one. Otherwise, it is not a linear one.
Okay. Okay, fine.
So if you are plotting, that means on the XY axis, if you are having the risk factor, magnitude of risk factor and disease outcome, simple XY plot. On your Y, you would be having the outcome, number of disease. And on the X, you would be having your risk factors levels, 1, 2, 3, 4 like that. And on the Y axis, you would be there having the disease. And by plotting the scatter plot, you are getting upward trend. That means that is your indication that you can use this test. But if you are not getting an upward trend, rather you are getting a parabola shape or you are getting a circular representation. Then in that case, you cannot use this.
Okay. Thank you, sir.
I think it's 5 baje. I'm not sure.
Okay.
Not enough.
Now one more test we are having, which we are calling it as a attribute. Okay. Sorry. So attributable risk is a difference in the incidence rate of disease between an exposed group and non-exposed group. Some author use the term risk difference to attributable risk. Attributable risk is often as percentage. Attributable risk is incidence in exposed minus incidence in non-exposed divided by incidence in exposed. Sorry, incidence in exposed. Okay, so your relative risk, odds ratio, these are the figures which do not take into consideration the proportion. What is the prevalence or proportion of the disease? Okay, but attributable risk is a risk which is giving you more information. It is telling you that if the risk is closed from your environment, this much prevalence of a disease can be decreased. Okay, but RR or OR is not telling these type of informations. Okay, but your attributable risk is giving this type of information. So although RR is very useful as a measure of relative importance to the disease of the risk factor, it does not tell us the overall importance of that risk factor. For instance, there is a study done by Khan and Sempos from the Framingham study that shows that RR of CSD to be 2.8 for those with systolic blood pressure of 180 or above, more compared to others. Whereas RR for cigarette smoking is only 1.8. Hence, it might appear that it would be more important to target health education to reduce hypertension rather than to use reduce smoking. So very interesting finding here we are getting. You can see that RR value, some subsample he has taken from Framingham study, and he finds that RR for CSD for systolic blood pressure of 180 or above is you are having a very higher risk, 2.8 times, whereas RR for cigarette smoking you are getting 1.9. So, but looking at this table, one can feel that it is very important that we should be more focusing on health programs rather than on focusing on the reduction of smoking. Okay, but what is the prevalence of the two? How many in the study? Later on, it was found that there are very few individuals who are having systolic blood pressure 180 or above, but there are very large number of individuals who were smokers. Okay, so instead, yeah, RR and RR is not taking into account of the prevalence. But once we are calculating the attributable risk, we are going to get the result that if your cigarette smoking is prevention for that, if someone is taking care of that, a larger proportion of individuals will be there who could be from where your disease, CSD disease, could be prevented. Okay. So what is required is a measure of combination of RR and prevalence of the risk factor. The attributable risk or etiological fraction does this job. So this will measure the proportion of cases of disease attributable to the risk factor. So it might happen that in a particular study design, you might get for a particular risk factor, you might get a higher value of RR. Okay. And 2-3 risk factors are there. first factor, you might get a higher risk factor. Second, you would be getting a little lower, but you might get a attributable risk for a second factor, which is having a lower value. You might get a higher value for that one because of the higher proportion of that disease.
Sir, can you explain attributable risk again?
Yes. Attributable risk, what odds ratio or relative risk, what they are doing is that they are telling whether the risk factor is really risk factor or not. Okay, it is not relating the disease with the proportion of disease which is present in the population. For example, in this case, suppose systolic blood pressure 180 or above are having 2.8 times risk of CSD, whereas for, let's not take it as a smoking, let's take it as for the diabetes. Okay, for diabetes, the RR we are getting it as 1.9, but will in the population, actual population, will you be getting larger number of individuals who are having systolic blood pressure 180 or above, or you would be getting larger number of individuals who are diabetic? What proportion you are going to get more? You would be expecting more.
Diabetic.
Diabetic. So that's what attributable risk will be telling us. Attributable risk is calculating, taking account of the RR in with relation to the prevalence also. Okay. So RR, OR and RR are giving us some incomplete information. From here it is, we might assume that it is very important to focus on the health education program. But for the same factor, we are calculating attributable risk, we will be able to see that much amount of risk can be controlled if we are focusing on smoking. So attributable risk is giving you, it is a combination of RR and it's a combination of with respect to the prevalence of the disease. This formula which we are getting, which you will find in most of the this one you will find this formula in most of the public health books, but there are some good books where you will find this formula, which is the formula of attributable risk only. This is the attributable risk denoted, where we are having, this is proportion of disease divided by total proportion, and this is your lambda. Okay, so your attributable risk is taking care of risk RR. It's a combination of RR and prevalence. Okay, so that's why it's more informative compared to your RR and OR. Based on RR and OR, can anyone tell that how much the if the exposure is absent, how much the disease will be controlled? You cannot tell. But if you have calculated the attributable risk and it is coming at to be say 30%, so you will be very confidently, you can say that if a particular risk is closed, okay, if you are able to control the particular risk, we are able to reduce the disease incidence by 30%. Okay, this type of a statement we cannot do merely on the basis of, we cannot give merely on the basis of RR or okay. Is it clear? Okay, these are some mathematical formulation for calculation of the 95% confidence interval for attributable risk. I'm not going into this because our software will be able to calculate this attributable risk. But how they are coming, this is the mathematical formulation with the help of which you can manually also calculate the lower limit and upper limit for your attributable risk. Okay, so we have done you can look at the prevalence. Here you can see if the prevalence is 1%. Okay, as the prevalence is going high, your relative risk value will be getting high. Okay, So for a lower value of attributable, lower value of your prevalence, you would be getting RR value, OR value, and attributable risk value more or less very close. But as the prevalence is getting high, you have to be very conscious for before making a statement about the disease and the risk factors. So this is the very first presentation which we have done, that is on the attributable risk. Now we can move on the specific type of study designs, that
How
is
do I get out of this?
case control and cohort study design.
Aditya ji.
Okay, now I would be starting with the cohort study design. Because before coming cohort, there is one important concept. Let's look into that. Confounding and interaction. Is the slide visible? Confounding and interaction. I hope the slide is visible. Confounding and interaction.
No, sir.
Yeah, it's not visible. Confounding and interaction.
No, sir.
No, sir.
No, sir.
Yeah, give me a second. Now, is it visible? Confounding and interaction.
Yes, sir.
Yes.
Yes.
Okay, I think many of you are knowing what type of the study designs are, but what would be the mathematical issues, or what are the conceptual issues which may arrive when you are trying to conduct these types of study designs? We are focusing on that things. So one of the important things which we have to consider while planning for a your case control study design or cohort study design is to consider the effect of confounding and interaction. Okay, so far we have concerned with only two variables, the risk factors and the disease status. Often a third factor may have an important influence on the apparent relationship between these two variables. If the third factor can explain at least partially this relationship, then confounding is present. So for instance, a relationship between the number of children and prevalent breast cancer for a sample of mothers may be explained by the age of the mother. Older mother tend to have more children and also have a greater chance of having contracted the breast cancer. Age is then a third factor that explains the observed relationship between number of children and breast cancer. Okay, so often what happens is that if you are having a cross tabulation between number of children born and breast cancer, and you may get a higher RR value or OR value, you are not considering the age factor. Okay, then you might have a impression that having a greater number of children may result in breast cancer, may be associated with breast cancer, but in actuality it is the age because of which you are getting this. Older the female, more chances she is having of getting the breast cancer. So if a third factor in your study design, if there is a third factor which is often not of your interest, but which directly or indirectly change your outcome or influence your outcome, then that factor is considered as a confounding variable. So if the third factor modifies the relationship between risk factor and the disease, then interaction is present. Okay, so if the third factor can explain at least this relationship, then confounding is present. And let me give you an example for confounding and interaction both, then so that it becomes clear. For example, if you are considering, say, MI, and you are studying the risk factor, say, alcoholism present, absent, MI, yes, no, and you have got a significant OR or RR value. Okay, but later on someone finds that okay, alcoholism is not related to MI, and what he has done, that he tried to recheck your data, and he find that he studied the alcoholic people, and he find that all the alcoholic peoples were chronic smokers. Okay, so the effect of on the MI which you are getting is not because of the smoking, it's because of alcoholism. So alcohol, because of smoking, so whatever the impact which you are getting is not because of the risk factor which you have considered, that is alcoholism, but is because of the third factor, which is your smoking. So here alcoholism is getting confounded because of your smoking effect. And interaction, what says? Interaction says, for example, we are having, say, hypertension and salt intake, and we have say we are considering it in male and female. So generally it is considered that if a male is there who is having lower salt intake, and a female is there who is also having lower salt intake, both are at lower risk, but somehow females are at more at lower risk compared to the males. Okay, or if we are considered in a other way, if a male is there who is having a higher salt intake, and a female is also there who is also having higher salt intake, but for the male we are getting a RR value of 1.5, but for the female we are not getting any risk. So in this case, the risk factor is, in this case, at the same level, because in this case what we are saying, we can see that gender and your risk, which is salt intake, are getting interacted. Okay, it's higher in males but lower in females in the same category. So that is interaction. So if this type of things are happening in your study, then we need to take care of these things. So how we can do that, we will see this. This is another example. Suppose that relationship between salt consumption and verbovascular disease stroke is quite different for men and women. Perhaps women with relatively high salt intake, that what I was saying, have moderate elevated risk of stroke compared to other women, whereas men with high salt intake have substantially greater risk than do other men. The sex would then be the third factor that modifies the relationship between salt and stroke. The sex would be said to interact with salt consumption in determining the risk of a stroke. The issue of confounding and interaction need to be considered whenever an epidemiological study is designed or analyzed. Consideration of likely confounding and interaction effect is necessary even before a study is begun, because analytical methods to deal with confounding and interaction can be applied if data on the specific third factors are collected. Okay, many times I have seen people are conducting a study and they want to establish an association between, say, diabetes and any certain other risk factors. Okay, so what they are doing is that they are only considering the variables in which they are interested. They are not considering other variables which might impact the diabetes. So if suppose in this previous example, if someone has not taken information on smoking, how one can rule out that whatever the thing is because of the you are getting is because of the alcoholism? You have, if you have taken account of smoking, alcoholism, MI and other factors, then only we can do stratified analysis and we can find that there is confounding effect or interaction effect. But if you have not taken the data of on the third factor, then you may not be able to take care of the confounding or interaction. So whenever you try to plan a study, you try to have as much information as possible on the risk factors which you are considering is of importance. Okay, there might be certain factors which you feel which are of not your interest, but you feel that they are related to the disease. In that case, try to have that information in your questionnaire. So in most cases, there will not be a single potential confounding variables. Thus, the term third factor could be referred. There can be more than one confounding or more than one interaction variables. So although confounding and interaction are very different phenomena, they are often confused. Part of the reason for this is that we may be unsure at the stage of designing a study whether a particular variable that we decide to record has confounding or interactive effect on specific relationship that we wish to study. Okay. The effect, the concept, already I have given the definition that what is confounding. Confounding is the variable which is of not our interest, but which directly or indirectly alters the outcomes. So how it is doing it? So what confounding can do? Confounding either can accelerate the risk. The actual risk is say 1.5, but because of the confounding, you might be getting it as 5.5. Or what it can do the reverse also. Okay, actually there would be a risk, a higher risk, 3 terms, but because of the confounding, you are not getting any risk in RR calculation. Let's look at the two hypothetical data to understand the concept of confounding. First situation, I would be showing you where there is lack of relationship, or where we are having where there is no risk, but we are having a higher risk. So this is a situation 1 where in actuality you are getting a higher risk. RR we are getting it as 5.52. Okay, so disease status is there, risk factor, exposed, non-exposed is there, and suppose we are having the disease lung cancer and we are having the exposure to say lifestyle habit. Okay, and say in lifestyle habit we are having good one and a bad one. Okay, and exposed, non-exposed, we are getting a risk risk of 5.52. Now we later on we find that there is a interactive there is a variable which we feel as a confounding variable, and in this case when we have done a stratified analysis, same data is there. You can look at 81, 80 is here, 1 is here, 29, 20 is here, 9 is here, 182, 180 is here, 2 is here, 28, 20 is here, and 8 is here. The same this data set which is of n is same. Okay, only thing what I have done is that we have stratified this data based on the confounding present or confounding absent, and then we are again analyzing the data. And here you can see that when the confounder is absent, we are getting no risk. When the confounder is present, then also we are getting no risk. So if we are not taking the consideration effect of the confounding, then we are getting a risk of 5.52, but in actuality there is no risk.
Sir, how this stratification is done? Like out of 81, one is to say like
this is a confounder variable. Okay, out of 81, suppose you have not considered the confounder variable, say smoking. So here would be smokers, smoking absent. Non-smokers, here would be smokers. And out of 81, there is one who is not smoking, and 80 are there who are smokers. Okay. So this relationship in this first table, this confounder variable is absent. Okay, so you have considered smokers and non-smokers in the same boat and you have done the analysis, but in actuality there is the smoking variable is there which is having an impact. And suppose in your data set you have not collected this information whether the individual is a smoker or non-smoker, then you cannot have this second table. Are you getting it?
Yes, sir.
So here you can see that same n is there. Only what I have done is that I have stratified this table based on the third variable, which I feel is a confounding variable. Now, second situation you can see RR. Give me a second. Yes. Now, you can see when considered within the levels of C, suppose the risk factor has absolutely no effect on the disease. The apparent relationship seen in table 1 is entirely explained by confounding. Now, thus number of risk of disease divided by number of people at risk. This is the relative risk formula. And if we are looking at this table, when confounder is present, this one, if you look at this table, here you would be, here you would be getting number of cases of disease 80 plus 8 divided by total 80 plus 8 divided by total, that is 80 plus 8 plus 20 plus 2 number at risk. And RR in this case, which we are getting it as non-disease one, 20 plus 2, 20 plus 1, 20 here and plus 1 here, 21 divided by total number at risk. So here we are getting whatever the risk, because the confounding, that is smoking here, we are getting 8 times higher risk. So when we think that we are seeing the effect of risk factor, but we may really be seeing the effect of C. Okay. So in actuality, the risk which you have considered is not the actual risk. Whatever the risk you are getting, that is because of the confounding variable. Is it clear, this one, how we have calculated? If you remember, do you remember the formula of this relative risk? Number of cases of disease divided on number of people at risk. Here we are calculating this RR is for the confounding variable. If we are considering confounder as a risk factor. So if we are considering confounder as a risk factor, what will happen? The risk present, the risk is present in this table. Risk present, how much disease? 80 plus 8 divided by total number at risk. Total number is at risk would be 80 plus 8 plus 20 plus 2. So 80 plus 8 plus 20 plus 2. Or in the second one would be number of people in where the confounder is absent. If confounder present, confounder risk is here risk in exposed divided by risk in non-exposed. So risk in exposed is where we have confounder present. So number of diseases 80 plus 8 divided by total divided by risk in non-exposed, where confounder is absent. So confounder absent, how much disease is there? 20 plus 1. This 20 plus 1 divided by total number, that is 20 plus 1 plus 9 plus 180. And here you can see that how much risk is there? It is 8. So whatever the risk which we have ignored, and here whatever the risk you are getting is because of your confounding. This 5 result is because of the confounder result, not because of the actual result, because of the this factor, exposure one. Is it not clear?
So, sir, how we will interpret this data?
This data is very straightforward to interpret. If you are looking at this data from this table, what you can say? You will be saying that the exposure is having the individuals who are exposed are at 5 times higher risk. है ना? Table number 1. By looking at this table number 1, you will be saying that the risk is at 5 times higher.
Yes, sir.
But once the data is this data, entire data set 81 plus 28, 29 plus 182. Okay. This data set, when you are this complete data set N, when you are studying further and you are segregating this data set based on a variable which you feel as a confounding variable. So you are segregating this data, stratifying this data based on the confounder absent, confounder present, and you are reanalyzing. Here you are not finding any association. Okay. Here 1 by 9, you are having a risk 0.1. 20 by 8, 1 by 9, which is 0.1. RR 1. 80 by sorry, 80 by 100, 0.8, 8 by 10, 0.8, 1. So you are getting a risk of 1. So this table number 2 is suggesting that this exposure which you are feeling, which is giving you a RR 5, is actually 5. It is 1. So how much is the confounding effect? From where this 5 was coming? This 5 we are coming because of the confounding effect. Now we can calculate the effect of confounder. If we are considering confounder as a risk factor, what would be the formula for RR? What will be the formula for RR if we are considering confounder as risk factor? So it will be expose number of exposed confounder exposed divided by number of disease confounder exposed divided by confounder non exposed. This will be the formula, na? Number of cases of disease in confounding present or risk in confounding divided by risk in not confounding. That would be the formula. The risk for confounding, number of cases of disease in risk, this is 80 plus 8 divided by total, and risk in non-confounder, that is 20 plus 1 divided by total, and this we are getting it as, this we are getting it as 8. Okay, so in actuality your risk factor is not a risk factor. Whatever you are getting, that is because of the confounder effect you are getting. Okay.
So there can be more than one confounder variable as well, na?
Yes, there can be more than one confounding variable.
Okay.
We have the methodology to deal with more than one confounding variable. I will tell you.
Okay, sir.
Okay. So confounding, when we think that we are seeing the effect of the risk factor, but we may really be seeing the effect of C. Now coming on the second situation. Here, table number 3, by looking at this table, you will be saying that there is no risk. 240 divided by 240 plus 420, 0.36, and non-exposed also we are getting 1. But when we are segregating this data based on the confounding effect, 240, 135 plus 105, 240, 200, 5 here, 195 here. Similarly, 420, 415 here, 5 here. And here you can see that when the data is stratified based on the confounding, you are getting a effect of confounder. You are getting the effect of the risk of the disease exposure. So here in actuality, you are observing that the exposure is not having any impact. But here what the your confounder is doing, your confounder is masking the real magnitude of risk, whereas here your confounder was what it was doing. Here it was doing a catalyst job. He was promoting that in actuality there was no risk, but he was overestimating the risk, and here it is underestimating it. It is masking it. Okay, in actuality there is risk. Okay, but your this confounder is not showing because of confounding effect. And now if you can find out the confounding effect, what will be the confounder? If we find out the RR in confounder, can anyone tell what would be the value? If we consider confounder as a risk factor, what would be the RR value? So it will be disease exposure in the confounder present, that is 105 plus 195 divided by total, and confounder absent 135 plus 5 divided by total. So here you can see 2.11. So here confounder is also having a impact 2.11, and your exposure is also having an impact 2.45. So what they were doing, they were canceling out each other. That's why we are getting it at a 1 value. Okay. Is it clear? Two situations.
Sir, what is the
Sir, how
interpretation
to
of
find out?
2.2, sir?
Please, one at a time.
What is the interpretation of the 2.2, sir?
2.2, that it 2.1.
2.11.
2.11, that is the relative risk if confounder is considered as a risk factor.
Is it the two people or two patients are that confounded absent, in the sense they are given not information?
No. 2.11 means that the individuals who are exposed to confounder are having twice risk, twice plus 11% higher risk.
Okay, sir. Okay. Thank you.
Yes, sir was saying something.
How can you find out the confounders while at the time of data collection? Can we do the stratification at the time of data collection also?
Yes, we can find out how to find out the confounder and how to consider whether the variable is confounding or not. Okay, so how to do this? We can.
Yeah.
I have a slide. It's quite far, but I can show you now. Okay, I will come on these things back. Yeah, look at these path diagrams. When this is your confounding variable, when the disease, this is D, this D is the disease and F is the risk factor. If you are having a third variable, if that third variable is directly related to the risk factor and is directly related to the disease, in that case, this third factor might be related as a third variable, which might act as a confounding variable. Okay, just say, for example, age. Stroke is directly related to stroke and is directly related to the hair graying. But here you can see that we are not having hair graying, arrow from hair graying to stroke. It is not leading to that. So causality is not there. But age is directly related to the risk factor and the disease outcome. Number of children, breast cancer, age. So if the confounding variable, if the third variable is directly related to the disease, but is not directly but indirectly related to the risk factor, then also the variable can be considered as a confounding variable. Now, if the variable is directly related to the disease and risk factor is also somewhat related to the disease, okay, and is somewhat related to the risk factor, for example, housing, renting, and CSD. CSD is directly related to smoking. Housing, renting may not be directly related, but may be related to CSD. This is, for example, in your certain area where you are having a lot of industry work is going on, and you are having a colony, nearby colony there. So there you can find the people of low socioeconomic strata. Okay, and there might be because of that SES, you might have some relationship with CSD, but it is not direct. And since the individuals are of low CSS strata, so somewhat there might be the relationship of smoking. Now, when C is not acting as a confounder, okay, when C is related to D, that is confounder is related to the disease outcome, but is not related to the risk factor F. In that case, your C will not be considered as a confounding. Smoking is related to CSD. High cholesterol is related to CSD, by high cholesterol is not related to smoking. So in this case, this red one will not be considered as a confounding variable. Second example, for example, C is related to the risk factor, and F is related to disease, but confounding is not directly related to the disease. For example, no fruits may result in low vitamin C level, and because of low vitamin C level, you might have scurvy. But no fruit is not related to scurvy. So here, this third factor will not be considered as a confounding variable. Third example, here you can see that when the third variable is a consequence of a disease. For example, smoking causes fibrinogen, and fibrinogen is causing CSD. In that case, this fibrinogen is not directly related to CSD. So it will not be considered as a risk factor. Here one arrow will be there, but smoking is directly related to CSD. So if your third factor is a result of a disease, in that case, or risk factor, in that case, it should not be considered as a confounding variable. Okay, I hope it is clear.
Yeah, it's very much clear, sir.
Okay, so now let me show you some examples how to do it, and how to do the calculate the confounder and interaction effect. Okay, using some good approaches. Okay, these are some other examples where we are having the effect of confounding. Okay, not identification of confounders. How to identify it? Now we shall consider what conditions are necessary before a variable may be considered a confounder. If C is to be considered confounder, it must be related to disease, but not be the consequence of the disease. Be related to the risk factor, but not be the consequence of the risk factor. So this, let us denote it by D, the risk factor by F, and the third variable as C, and what we have discussed now, the same thing. So this is the path diagram for C acting as a confounder, and when C will not be considered as a confounding variable. Okay, so these are the strategies. Okay, what makes something a confounder depends upon data-based observation relationship and a prior knowledge. The below figure summarizes the necessary condition to decide which variables are potentially confounder. So if C is related to D, or they are directly related or indirectly related, and C is related to F, or directly or indirectly, in that case, your C will be, third factor will be considered as a confounding variable. But if C is a consequence of D or C is a consequence of F, in this case, it will not be considered as a confounding variable, your third factor. Is it clear to everyone?
Yes.
Okay. Okay, there are few standard approaches to ascertain the confounding effect and interaction effect, and so we would be discussing some standard approaches. So one is using estimation method. So we can assess confounding by estimation method of the risk factor with and without allowing for confounding. For instance, in table number 5 and 6, RR for renting is 1.43. This table we have not solved this table. So suppose CSD and housing tenure, we are considering this and we are getting a RR of 1.43. And suppose we have considered the third factor, that is smoking, as the confounding variables, and we have got a value of risk as 1.27 and 1.33. Okay, so here it is a risk, that is a housing tenure, and when segregated with respect to smoking, then also we are getting a higher risk, 1.27 and 1.33. Okay, so in this variable, so we want to find out how much effect of confounding you are getting. So table number 5, when unadjusted, we were getting a risk of 1.43 and around 1.30 for both those data. That means for confounding and non-confounding. So then the effect of confounding we can calculate by using this formula, EC, that is the risk when confounding is present, divided by E, when the risk when the confounder was not present. So when the confounding was present, we are getting 1.30. We are taking the average. This table, 1.27 plus 1.33. So we are taking the average, we are getting it as 1.3. And when there is confounding is not considered, we are getting 1.43. So percentage of confounding, how much we can calculate? EC by E. That is 1.30 divided by 1.43 into 100. This which we have done. EC when the confounder was present, average value 1.3, and when confounding is not present, 1.43. So this we are getting it as 0.0091. Okay, 10 is more. It's 0.091, I think. 1.90 divided by, sorry, 1.30 divided by 1.43. So we are getting 0.9. Here we are getting it as 0.909. Okay, calculation mistake is there. So how much the confounding has an effect? 9%. Okay. The similar, you can find out the confounding effect in the first two table also using this estimation method. Okay. Now, other method for finding out the confounding effect is given by mental and Hengels. Okay, so we are going on that estimation directly. Okay. Now, so that standard method can, as you people were asking, that there can be more than one confounder. So if there are several confounders, how to find out the real effect? Okay. For example, if we consider smoking, yes, no, exercise coded as seldom, sometimes, often, very often as confounder. For the relationship between housing tenure and CSG, table 6, we would define across 4 8 strata and corresponding subtables. And in that case, how we can find out the confounding of table number 6. Let's go in the table number 6. This is the table number 6. Okay, housing tenure is there and smoking effect is there, and we want to find it out the for more than 2 confounding effects. How we can calculate it? So we can calculate it using mental Hengel approach. Okay, mental Hengel approach, let me show you here. So using mental Hengel approach, we can calculate it. So this mental Hengel approach is using this formula, summation AIDI by NI by summation BICI by NI. Okay, so for each strata, we would be calculating the adjusted odds ratio, and for the exposed group and for the non-exposed group, and we are taking the summation over the entire strata range, and then whatever the value we would be getting, that would be the adjusted odds ratio value. Okay, let's look at this example. Here we are having smokers, non-smokers. Smoking we are considering as the your confounding variables, and using mental Hengel approach, if we have to solve it, it will be for this non-smoker table. If we have to calculating AIDI, that is 33 into 1722 by ENI, that is 2726, divided by BICI, which is 923 into 48 divided by 2726. That will be for your non-smokers. Similarly, we can do it for the smokers. That is 52 into 678 divided by ENI, which is 1657, and 989 into 29 divided by 1671. So we can calculate the odds ratio for confounding effect. We can, if we have to find out the confounding effect, so we can use the OR adjusted divided OR crude divided by OR adjusted. That means one time you can use the odds ratio general formula which you are using, AD by BC, and for the confounding effect you can use the mental Hengel, that is the OR adjusted one, AIDI by NI divided by BICI by NI, and then you can find out the actual confounding effect. This is another example. Here it has used the crude measure. So using crude measure, 29,1607 divided by 135 into 205. you can calculate it and you will get the odds ratio as 1.68. Okay, 29 into 1607 will be the numerator. AI into DI divided by BI into CI. So you are getting a crude measure at 1.68. Now we have to find out the adjusted measure. Okay, so adjusted measure. Now we have segregated if we feel that age is a confounding variable. Okay, so here age is a confounding variable. So we have divided the age group into different categories 1, 2, 3, 4, 5. And now we are calculating the adjusted measure. Okay, so this is for the first age group, cumulative age group, and for the different age groups, if we are calculating it, we are getting the crude values AI into DI by NI. Okay, so totally here it is not given. This is diseased, non-diseased. Here it will be total AI DI 4 into 2 to 4 divided by 62 into 42. This is the crude measure. This is the crude measure. All these are the crude measures which we are getting. Now mental hinges, if we are using it, then we can have AI into DI divided by NI. First one for cumulative, all the values. That is for the AI into DI, for the first one, it is 4 into 224 by NI, this total. 4 to 62, 24 plus N into 390 divided by 33 into 12. Similarly for the third values. So for all these values, we can have the adjusted odds ratio, and we would using mental Hengel test, you can get the values. Okay. So similarly, we can have, as we are having the mental Hengel estimate for OR, similarly, we can have the mental Hengel estimate for RR. So for this, we are having this formula AI in the first estimate, EI non-exposed divided by NI, CI, EI, that is the non-estimate divided by NI. And we can have for the mental Hengel estimate, we are having this standard error formula, and you can calculate the 95% confidence interval for this mental Hengel estimates also. Okay. Now to find out, this was all about confounding, which we are talking about. Now we can have find out the effect of interaction also. Okay, so for interaction, to find out the effect of interaction, we are using a different approach which was given by Cochrane and mental Hengel. Okay, so this test statistics of no association can be based upon the test of expected cell values. In this case, we are using this test statistics, which is this one, AI minus summation EAI minus half divided by VAI, where we are calculating these values EAI, that is expected cell values, which is nothing but column total into row total divided by total number of observation, and this is the variance of this value. So we are calculating it, and we are using this test statistics. We are getting the value of this value. So from table number 6, if we are calculating, so table number 16, A1 value which we are getting is 33. Table number 6, this one. Sorry. This is the table number 6. So AI value you can see that is 33. So we will find out the expected values, which is row total 956 by column total, which is 81 divided by grand total, which is 2726. So you can see that we would be getting the same one, 33, and EA1 we are getting an expected value, we are getting it as 28, and variance of this value we are getting it as 79. Similarly, A2 value is 52, expected value we would be getting 46, and variance value we are getting it as this much. And using Cochrane and mental Hengel test statistics D, if we are tabulating this test statistics and we are comparing this test statistics with chi-square distribution, chi-square table with at 1 degree of freedom, and if our null hypothesis is rejected, we would be saying that there is a interactive effect. So mental Hengel approach is based upon the assumption that the parameter representing the comparative chance of disease does not vary by levels of the confounding variables. Okay. So whenever you are using a mental Hengel test, okay, mental angel test is exclusively based on for confounding variable only. If the variable is third factor variable is not confounder variable, it is an interaction variable, then you cannot use the mental angel approach. So first what we have to do is that first, once your data comes to you, you have to apply Cochrane and mental angel test. This is a test for the interaction variable. And if this test is rejected, is not rejected, that means each level is equally important. Each level is equally important, then you can test for the third vector. You can consider the third vector as a confounding variable, and you can apply mental angel test. But if this test is significant, that means there is a interaction effect. That means your risk and your levels are interacting. Okay, and your third variable is a interactive variable. It is not a confounding variable. So often your third factor, if it is an interaction variable, it is more difficult to control. If the third variable is confounding variable, we have seen we can do adjusted analysis. But if the third variable is an interactive variable, then we have to use some DOE experiment to find out the interaction effect, and direct interpretation in that case is little difficult to find. Okay, so this one is on confounding and interaction. Okay, so we are done with the confounding and interaction. Okay, anyone is having any query with respect to confounding and interaction can ask. Yeah, I agree. Someone has written that it's very lengthy. Yes, I agree. Recently, we are conducting a workshop on this epidemiological study design, and it is of 7 days for this study design only. So I agree that it is very, very lengthy, and each study design requires at least 1-2 days. So that is true that it is little lengthy. Okay. Okay. Kindly explain in SPSS. We are explaining it in SPSS in our workshop, which will be from 2 to 8. But next time, whenever we would be conducting it, you probably can also join. And here also, if people are giving this hands-on opportunity, I would be love to share my experience with that thing. Okay. So I think the time is from 6 to 8, and we are almost done with that thing. Okay, so I'm sorry, but it is not covered. Biases are left. Even in the case control, there are certain things which are left, but it is not possible to cover everything in this small lecture. So whatever the technical issues and whatever the practical issues which one will be feeling in the study design while planning it, will have these things. So I think I am done. If someone is having a query, can ask me.
Dr. Ashish, sir.
Yes.
I'm Dr. Ayurvatan. You have explained very much for medical student. Can you explain salient features for researchers in the medical field? You have explained the whole statistics, I think. What can we can do for as a medical researcher in this?
Yes, I think that key. I admit that it is. I have done little injustice, because the thing is that study design is very complicated thing, sir. The thing is that key whenever if you focus on the flow chart which I have given. Okay, many times I have feel that people are just taking the study design that this will be my this is for case and control. It is up to that, it is okay. This is the case, diabetes one I'm considering as a case, and their family members who are non-diabetic I'm considering them as a control. It is fine. But when we are considering talking about the exposure, they are having a lot of confusion. Let me give you a practical example. And one of student in endo in our department, in our college IMS, she has considered the same thing. And she has taken diabetes as a case and the family other member as a control. And she has considered the disease, one of the disease consequence, as a exposure variable. Okay, so destruction of the pancreatus, which she has considered as exposure variable. So here the destruction of the pancreatus in diabetes, it is the disease consequence. It should not be considered as a risk factor. Okay, so as I have given you the flow chart, in that flow chart you try to remember that if the risk which you are considering is a consequence of the third factor which you're considering is a consequence of the disease or is a consequence of the risk factor, it should not be considered. So before planning a study design, we need to study the things very thoroughly about the confounding, about the interaction, then we can do, because all these things are done using softwares, and softwares are innocent. They will give you anything, whatever you give them, they will give you the output. But the thing is that we should, whenever we are planning, we should try to make our questionnaire elaborative one. Try to have all that third factors which are related to the disease or the risk factor in our study design, and then we try to do the cross tabulation. First basic thing is that you do a cross tabulation and try to find out the chi-square. Do a scatter plot, then go for a regression analysis. So these are the basic things when we have to consider. Try to have as much data as possible. Try to have some basic descriptive statistics, then go for a higher analytical studies.
Thank you, Dr. Ashish. Thank
you. Anyone else?
डॉक्टर आशीष, एक क्वेश्चन और पूछना चाहूंगा मैं।
हाँ पूछिए सर प्लीज।
कि आपका जो है कि मेडिकल रिसर्चर को क्या बताना चाहेंगे एक पॉइंट के कंपाउंडरों को खत्म करने के लिए, कम करने के लिए आप क्या करें डेटा कलेक्शन के समय? तो क्योंकि ये भाई मैचिंग जो स्टैटिक्स है वो तो मैं नहीं कर सकता सर।
हाँ नहीं, वही मैं बोल रहा हूँ कि एक आपको क्या करना है, जैसे आपकी साइंस सर स्टैटिस्टिशियन को नहीं पता है। आपकी साइंस आपको पता है कि ये रिस्क फैक्टर है, ये डिजीज है, तो आपको क्या करना है कि आप जो रिस्क फैक्टर कंसीडर कर रहे हैं उनको तो लेना ही है, उसके अलावा अपने आपके डिजीज से रिलेटेड और जो रिस्क फैक्टर हो सकते हैं आपके इंटरेस्ट के नहीं है लेकिन डिजीज से रिलेटेड है, उनको भी अपनी स्टडी में इनकॉर्पोरेट करना रहेगा। तभी आपका स्टैटिस्टिशियन जो है कंफाउंडिंग वेरिएबल, कंफाउंडिंग इफेक्ट निकाल पाएगा या इंटरैक्शन इफेक्ट निकाल पाएगा, अदरवाइज वो नहीं निकाल पाएगा। तो आपको क्या करना है, आपको वो रिस्क फैक्टर्स को भी लेना है जो आपके इंटरेस्ट के तो नहीं है लेकिन वो डिजीज से रिलेटेड है या आपके रिस्क फैक्टर से रिलेटेड है, उनको भी आपको अपनी स्टडी में लेना चाहिए।
क्या हम इसमें मैचिंग कर सकते हैं दोनों की तरफ, दो ग्रुप में? तो
अगर हमारा केस कंट्रोल स्टडी डिजाइन है तो मैचिंग तो मैंडेटरी है, करना ही चाहिए। जैसे दो फैक्टर्स हैं जिनकी मैचिंग हमेशा करनी चाहिए इररिस्पेक्टिव ऑफ द डिजीज और द रिस्क फैक्टर। वन इज एज एंड द सेकंड वन इज जेंडर। तो एज और जेंडर की मैचिंग हमेशा ही करनी चाहिए।
सपोज थर्ड फैक्टर है उसकी भी मैचिंग हम कर दें तो
थर्ड फैक्टर की तो मैचिंग करें ही। अगर आपको ऐसा लगता है कि थर्ड फैक्टर ऐसा है जो कि डायरेक्टली और इनडायरेक्टली आउटकम को अल्टर कर सकता है तो उसकी भी मैचिंग करिए।
और जो आपकी जो कोहॉर्ट डिजाइन है इसमें कैसे कम करेंगे इसको?
कोहॉर्ट डिजाइन इसीलिए आप देखिए कि हियरार्की में, स्टडी हियरार्की में सबसे ऊपर हमारे पास सिस्टमेटिक रिव्यू एंड मेटा एनालिसिस है, आरसीटी है, और उसके बाद कोहॉर्ट स्टडी डिजाइन है। ठीक है, कोहॉर्ट स्टडी डिजाइन इसीलिए ऊपर है क्योंकि उसमें बायसनेस कम होती है। तो कोहॉर्ट स्टडी डिजाइन की अलग क्राइटेरिया है। कोहॉर्ट स्टडी डिजाइन अगर आप कर रहे हैं तो आपको क्या करना है कि कोहॉर्ट को ये इंपॉर्टेंट है आपके लिए कि कोहॉर्ट को आप ऑब्जर्व कितनी बार लंबे टाइम तक कर पा रहे हैं क्रिटिकली। ओके, अगर आप ये हुआ कि एक बार, बहुत लोग क्या करते हैं कि हम कोहॉर्ट स्टडी डिजाइन कर रहे हैं, एक बार स्टडी के शुरुआत में देखा, एक बार बीच में देखा और फिर उसके बाद 4 साल बाद आखिरी में देख लिया। तो ये इस तरह की जो कोहॉर्ट स्टडी डिजाइन कर रहे हैं जिसमें विजिट ही बहुत कम हो रही है, these are actually not a cohort study design. So in that case, it is very important to have a continuous scrutiny over the subset which you are.
I'm practicing emergency medicine, sir. We have
Yes.
short cohort also. Suppose I give the anti-epileptic drug to any epileptic patient and study after 5 minutes. This is also a cohort study. So
come again, please.
हाँ, अगर मैं किसी पेशेंट को अपने जो एपिलेप्सी का पेशेंट इमरजेंसी में आता है उसको मैं एंटी एपिलेप्टिक ड्रग देता हूँ और उसके आउटकम को आफ्टर 5 मिनट देखता हूँ, दिस इज आल्सो कोहॉर्ट स्टडी ना?
नहीं, आप उसको दे रहे हैं, आप उसको ड्रग दे रहे हैं ना?
ड्रग दिया, मैंने एक्सपोजर दिया उसको, अब उसके साइड इफेक्ट को आफ्टर 5 मिनट बाद मैं देखता हूँ।
नहीं, आप तो इंटरवेंशन आपने कर दिया ना, आपने तो ड्रग दे दिया उसको, तो इंटरवेंशन कर दिया आपने।
नहीं, मैंने ड्रग दिया नहीं, मैंने मेरा साथी ड्रग दे रहा है, मैं ऑब्जर्व कर रहा हूँ।
जो भी है, मतलब हमारे कहने का मतलब सर ये कोहॉर्ट स्टडी डिजाइन में क्या है कि इंटरवेंशन जो भी पीआई या है उसके एंड से नहीं है। कोहॉर्ट स्टडी डिजाइन का जो मतलब है कि आपके पास एक ग्रुप ऑफ कोहॉर्ट है, आप उसको ऑब्जर्व कर रहे हैं, एक्सपोजर हो रहा है, नॉन एक्सपोजर हो रहा है, और फिर आप डिजीज का आउटकम मेजर कर रहे हैं। यहाँ आप तो डिजीज उसमें इंटरवेंशन दे रहे हैं उसको, या आप या आपका जो भी कोलीग है सर।
नहीं, सपोज जैसे मेरे पास आईसीयू का कोहॉर्ट है 10 पेशेंट का, इसमें सेडेशन एनालिसिस करनी है। सपोज सबको प्रोपोल दिया गया और उसको ऑब्जर्व किया गया आफ्टर 10 मिनट, तो दिस इज आल्सो कोहॉर्ट स्टडी।
नहीं, आपके पास 10 इंडिविजुअल्स हैं, उनको आपने
10 पेशेंट का एक मैच्ड कोहॉर्ट है हमारे पास।
मैच्ड कोहॉर्ट है।
हाँ, दिस आईसीयू 10 बेडेड आईसीयू and or we want to plan the effect of sedation in patients after 3 hours, suppose. So this is also cohort study or not?
No, it's not a cohort study, sir. It's not a cohort study. If you are doing a matching that with respect to some risk factor which you are considering, you can have it as a case control study design, but it's not a cohort study design. Cohort जैसे ही बोल दिया तो group of individuals generally healthy and sharing some common attribute, जैसे कि हम बोलते हैं बर्थ कोहॉर्ट, कि एक साल में जिस सेम ईयर में पैदा हुए बच्चे हैं उनको हम फॉलो कर रहे हैं, ठीक है। इसमें जैसे आप कर रहे हैं कि 10 लोग हैं जो कि डिजीज्ड हैं, सेम तरह के कैरेक्टरिस्टिक्स हैं, उनके लिए आप सिमिलर टाइप ऑफ मैचिंग कंट्रोल ले लीजिए, और फिर उसके बाद में आप डिजीज हो गया है ना इन लोगों को।
डिजीज नहीं, एक्चुअली हम जो मेरा एक्सपोजर है वो है सेडेशन, आउटकम है मैं इनकी सेडेशन एनालिसिस करना चाहता हूँ। तो सेडेशन
आउटकम क्या है?
sedation analysis is the outcome. Suppose BIS monitoring, we do the sedation monitoring by the BIS. So BIS is the outcome and sedation is the exposure.
Sedation is the exposure. Sedation is the exposure. BIS is your outcome.
Yes.
Analytical cross-section.
नहीं, ये सर ये नहीं है, आपका कोहॉर्ट नहीं है, बिकॉज पहला तो चीज है कि कोहॉर्ट में एक्सपोजर इंटरवेंशन नहीं दिया जाता है। दूसरी चीज ये है कि इसमें कंट्रोल भी नहीं दिख रहा है, तो इट्स नॉट अ कंट्रोल, केस कंट्रोल आल्सो, यू कैन हैव इट एज अ क्रॉस सेक्शनल स्टडी डिजाइन।
Okay.
थोड़ा सा बात देख रहे हैं कि आउटकम क्या हो
Sir,
रहा है।
only last question. Can you please explain case control study?
केस कंट्रोल स्टडी।
Yes, sir. Yes, sir.
केस कंट्रोल स्टडी डिजाइन में मैम क्या होता है कि वी ऑलरेडी हैव द केसेस,
Yes.
the individual is already a diseased one, and we are retrospectively asking him whether the individual was exposed to the risk factors. There can be more than one risk factor.
I also want to ask
modifier.
one question.
So effect modifier and that one is confounding factors and interaction factors you have discussed about. Please give a light again.
Yeah, confounding variable, as I have told you, is that confounder variables are those variables which directly or indirectly alter our outcome. For example, जैसे हम लोगों ने in discussion I have given that MI and alcoholism, we are getting a significant result, but all these result when we have stratified with respect to smoking, we are getting that we are not getting any effect. Whatever the effect you are getting, that is because of the effect of smoking. Okay, so here it is all the effect which we are getting is because of smoking, not because of alcoholism. The third factor is modifying the association. So this is confounder. And effect modifier or interaction is what?
So both these two are same. Effect modifier and interaction.
Yeah, effect modifier and interaction are both are same. Both are same. Okay. So interaction says that at different levels of risk factors, you are getting different risk. Males and females, same level of exposure, but different level of risk. So the risk is interacting with the this levels of exposure.
So basically, we can say that confounding factors are directly or indirectly affecting the factors as well as on the outcome. And whereas the effect modifier is just having influence over outcome only.
Are having different impact on the levels of exposure.
Okay.
So we have to, what first we have to do? We have to first check the interaction effect that we can do using Cochrane and Mental-Hengel test. Again, if that hypothesis is rejected, then we go for to check the confounding effect, which we do using the Mental-Hengel test.
सर कोहॉर्ट स्टडी में सर कौन सा एनालिसिस लगेगा सर?
कोहॉर्ट स्टडी हमारी बहुत अच्छी स्टडी होती है, उसमें हम आरआर से भी कैलकुलेट कर सकते हैं सर, ओआर से भी कैलकुलेट कर सकते हैं। और हमारा स्टडी डिजाइन, अगर ये जो कंफाउंडिंग और इंटरेक्शन का बात है, ये दोनों ही स्टडी डिजाइन में आएगा और दोनों को ही हैंडल करने के लिए हमारे पास टूल है। कंफाउंडिंग को चेक करना है तो मेंटल-हेंजल, इंटरेक्शन को टेस्ट करना है तो वो कोकरेन एंड मेंटल-हेंजल से कर सकते हैं। I have few more questions in the chat box also. I'm seeing it. Kindly share your number. Okay, you can have my number from. I have given my contact in this chat box, or you can contact Dr. Dharmendra also. Anything else? Cross-sectional analysis I have not covered because of the limited time. Cross-sectional analysis is not difficult one also. It is very easy. You can generally we use same tools in the cross-sectional study design only, except RR cannot be used. OR can be used.
So you have made the table for confounding. So what is the method of splitting the table? Stratifying.
Stratifying means we are doing the cross tabulation. You have considered the same number of individuals, 100 individuals were there. Okay, and we have classified them as diseased, non-diseased, and say alcoholic, non-alcoholic. But these individuals are again stratified in the light of smokers and non-smokers. So what we are doing it as, first we are classifying them as smokers and non-smokers, and within smoker we are classifying them as alcoholic, non-alcoholic. Here also we are in the non-smoker also alcoholic, non-alcoholic, and then we are seeing the disease. Okay, and if then we are doing the OR or RR calculation. Okay. So first we are stratifying with the third effect, then the effect variable of our interest.
Thank you. Thank you.
Thank you. So for hands-on, you people can on the university website we have this workshop link, our workshop link. You can, if you can join for that, have more exposure. Please give a reference of a simple one statistics. There are many books, but you can consider a book by simple by Abhendra Answer. It's a good book. Or you can have a book from simple biostatistics by Douglas and Altman. It is also a very good book.
Sir, one question regarding odds ratio.
Yes, please.
Sir, as you said that it is preferred for retrospective study. But when there is some cricket match or say horse racing, they always show their, tell their win or lose percentage as a odds ratio. Why it is so?
Because in horse race, I can tell you that people are calculating the probability of winning the horse by losing the horse. This is the odds happening divided by non-happening. Okay. So sometimes same thing is there. Both the things are measuring the risk, but sometimes people try to have a relative figure. Okay. So if someone is trying to have a relative figure, then they are going with a odds ratio approach. But sometimes one wants to have a direct probability approach. What proportion are there which are having higher risk? In that case, people are going with the relative risk. Okay. And generally in relative risk, we are having a formula where it is measured on the new number of cases, incidence in exposed divided by incidence in non-exposed. So many times it is not possible to have. That's why we often go with the odds ratio.
Excuse me, sir.
Yes, please.
Can you suggest the book name of the book?
For this study design?
No, you have told just now.
The book for simple biostatistics, you can have the book from Dr. Abhay Indrayan, Simple Biostatistics by Dr. Abhay Indrayan. And there is a book by Douglas Alterman, Simple Biostatistics.
Okay, thank you.
Okay, I think Dr. Dharmendra is there. Hello.
Sir, in cross-sectional study,
yes,
when we want to compare the data, which means which type of chi-square or ANOVA, which we will apply?
Very different things. If we are having a cross-sectional study design and your objective is on your outcome variable is you are interested in the mean values. Okay. And if you are having more than 2, in that case, we go for a ANOVA test. Okay. But if you are conducting a cross-sectional study design and you are interested in proportions or count values, disease, present, absent, like that values, count values. In that case, to test whether there is any association or goodness of it, we do it using cross-sectional study design. If we are using mean, we can go for a ANOVA.
Actually, I am testing the effect of that some devices which is used in protection in blue lights while working on computer.
Okay, so the value which you are getting, that is a absolute value or count observations you are getting, categorical count or continuous?
Actual categorical only.
Categorical value. So in that case, you can go with a chi-square. If you are getting the actual values, then you can, if you can calculate the mean, if mean is sensible in your case, then if you are having more than 2 groups, you can go with the ANOVA. For 2 groups, you can go with the t-test, given it follows the parametric test. Okay. Thank you.
I think time is over, sir.
Okay, I think can close it. Okay.
Yeah, sir. Thank you. Thank you so much, sir.
Thank you. Thank you, everyone.
Thank you.